So let's have a look at pumps. Now this is something that's very, very common in the water industry. Used to move water around. There's pumps that are used for water systems and pumps that are used for wastewater. They're actually a bit different, but they're both primarily what are called centrifugal pumps. Okay. So what pumps do is they move water. They use power from a motor to make two things. One is pressure, which we measure as head and feet, and the other is flow. Okay, so different pumps will split that power from the motor in different ways. Some are high pressure, low flow. Some are higher flow, lower pressure. But the power from a motor is split between doing those two things. Generally speaking, in this industry, we use centrifugal pumps. They have a spinning impeller that's enclosed in something called a volute. Okay, so this is called the impeller right here. It spins on a shaft that's driven by a motor. It's enclosed by what's called a volute. That's the case that fits around the impeller and gives the water somewhere to go. So the water would enter this pump kind of from in front of the page. So the water would come in this way. It would hit the center of the volute coming in kind of perpendicular to the page, and then it would be thrown out. The impeller will throw it out along the volute. It'll work its way around the perimeter and go into your discharge pipe. That's basically how that works, right? So the impeller is the device that takes the energy out of the motor and transfers it to the water. So there you see a pretty standard pump setup. There's the motor, that's what powers it. And what we're looking at here, of course, is the pump right there. And then you see this case here, which is called the volute. Okay. Right there. Now, impellers look something like that. There's two basic types, you might say. The one on the left is an open impeller, which is less efficient, but does not as prone to clogging. So that would be used on wastewater, where you might have things in the water that could clog a pump. The one on the right is closed. It's got a plate on either side, which makes it more efficient because it directs the water in exactly the direction you want it to go. But of course, that can only be used for clean water because that would clog up pretty easily. So you have, water pumps on the right there use that type of volute or impeller. You can see them up in the high 80s for efficiency, maybe even into the 90s. The open impellers are used for wastewater. There you're looking at efficiencies down around 50% or so. So the design of the impeller affects the efficiency of the pump. Okay. So there's a pump that's cut open with an open impeller in there. So that looks like a wastewater pump to me. So what's going to happen here is the water is going to come in this way through a pipe. It'll hit that volute, the impeller, and be thrown out along the volute, and then it will come on up the discharge piping like that. That's the path of the water. The motor would sit back here and drive this. So that's the motor. Okay. Okay, there's a closed impeller. Same sort of deal here. That's an impeller that has a plate on either side which encloses it. That one's opened up a bit more. It's harder to see, but you can see some of that open space where the water's running in the volute there. So here's the impeller. Okay. So what the impeller does is it spins and throws the water outward, and it gives the water velocity head. Okay, so that's the form that the energy takes. It's being delivered to the water. It starts off in velocity. The volute channels the water into a spiral shape. Okay, so what you're going to have here initially is velocity. Now this thing works on a Q equals VA principle. So as you work your way around the volute, the space opens up a little bit. A volute is usually in a spiral shape. So as the A goes up, the velocity decreases as you work your way around. Now the energy has to go somewhere. The energy's in the water. It's just the velocity head goes down because the velocity decreases. So what happens when you're coming over here is you develop a lot of pressure. What the energy does is it changes from velocity head into pressure head, and then it moves out the pipe. Okay? That's the idea on the design of a pump. Okay? So when you are rebuilding a pump, if you ever do that, you do want to be sure you get the impeller put in properly, okay? And that's I don't know how common a mistake it is, but it's something that people talk about. If they put the impeller in backwards, you end up cupping the water. You don't want to do that. This impeller here is designed to spin that way so it throws the water out. You don't want to have the impeller turned around going the other direction because it'll cup the water and it won't throw it out and the pump won't work properly, okay? So just one thing to remember when you're rebuilding a pump. Get the impeller in properly, okay? Okay, so the one on the left is actually the one that's right. That's how you put the impeller in. The one on the right is incorrect. That's not how you put that in, okay? That's shown on page 130. So we're doing all right with that? Okay. All right, now one of the basic parameters here is the rim speed, because that's the speed on the rim of the impeller. How fast the outer edge of the impeller is spinning. The faster the tip of the impeller moves, the greater the velocity and the greater the velocity head. Okay. So the rim speed is the angular speed of the impeller, which you can think about as being RPM. That's what you read on your tachometer in your car, and you can hear that quite often as a motor revs a little bit, times the circumference of the circle that the impeller travels in, which is 2 pi r. So if you take RPM, which is the angular speed of the impeller, the revolutions per minute. A revolution is 1 turn of a circle. So an RPM is revolution per minute. If you then multiply that by 2 pi r, that's the circumference. What you get is the rim speed. Okay. So that's the basic way you can figure out what the rim speed is of the pump. The rim speed then creates velocity head, and that's what gives the water energy. Okay. So you can deliver the same rim speed in different ways. You can have a small impeller spinning at a high RPM, or you can have a large impeller spinning at a lower RPM. They both would deliver rim speed. So I just had a couple examples there of different sizes of impellers that you could have. So 6-inch or 12-inch, and then spinning at different rim speeds. All right, so if you've got a 6-inch impeller spinning at 3,500 RPM, so that's 3,500. RPM is revolutions per minute. You can then multiply that by 2 times pi and then times r. Now the radius of a 6-inch impeller would be 3 inches, which is 0.25 feet. Okay. 6-inch impeller, half of that is 3 inches. So what I'm doing there, I'm taking 6 inches over 2 is a 3-inch radius. and then 3 inches over 12 would get you 0.25 feet. That's how I'm calculating that out. Okay. So if you take 3,500 RPM times 2 times pi times 0.25, you get the rim speed, 5498. And that would be measured in feet per minute. Okay. So we're doing all right with that? We're just going the angular speed times the circumference. And that gets you the actual velocity. The way we're going from revolutions to feet is we're saying that 1 revolution is equal to 2 pi r feet. Okay, because that's, so I guess to really follow my units through, I guess I could put 1 revolution down here.
Yeah, can I just say the same as pi times pi?
Oh, okay. Yeah, same thing. I mean,
Yeah.
it all kind of comes out. Okay. All right. Now we could do the same thing for a 12-inch impeller. Okay, so 12 inches over 2 will get you 6 inches. 6 inches over 12 gets you half a foot for the radius. So if we got 1750 revolutions per minute, and if we know that 1 revolution gets us 2 times pi times the radius, which is 0.5 feet, I guess I'm dividing by 2, then multiplying by 2. I guess that's extra work in it. So, all right. That will get me the rim speed for this one. So 1750 times 2 times pi times 0.5. And see, that gets me the same number. So this just demonstrates how you can get the same rim speed in different ways. All right.
Just notice that there's a typo in the 12-inch versus
Oh, there is?
it says 0.1 feet.
In typo in the slide or the book or both?
Actually, there's both.
Oh,
Looking at the slide in the 12 inches or 0.1 feet.
oh, sure enough. Yeah, okay, thanks.
And the calculation is correct.
Yeah, it all comes out in the wash, but yeah, you're right. So there's an error in here. It's in the book too. That should say 1 foot. Okay, so that's one just kind of quick calculation you can run if you're inclined to do that. It's an idea of the rim speed. And then there's another one there that'll tell you basically to find the head developed by a pump. Okay, it's the diameter of the impeller in inches times the RPM divided by 1840 squared. All right. So if we look at what we were just looking at, let's take the second one we did where we had a 12-inch impeller. Okay, so the head for that would be the diameter of the impeller in inches. That would be 12 inches. Times the RPM, which was, I think, 1750. Okay, divide that by 1840. and then square everything. And that should get you the head that the pump develops. Okay, so that'd be 12 times 1750 divided by 1840. And then you could square that. So this pump in that example would deliver about 130 feet of head. And that has to do with how high it would raise the water. That's something on the order of about 56 psi is what that pump would deliver. Okay, so we're doing all right with that? Just some basic kind of what sort of ballpark my pump's in kind of calculations here for some of this. Okay. So this particular pump that we have is going to deliver 130 feet of head at 1750 RPM. All right, now keep in mind that a pump, the power delivered to a pump is split between pressure and flow, head and flow, pressure and flow, whatever you want to call it. Now, there's different kinds of pumps. A typical pump doesn't have a governor on it. It doesn't have a throttle. You just turn it on and it goes. So what you try and do is match the design on your pump to the job you have to do. Now, a lot of pumps these days have things like variable speed drives on them where you can change the characteristics of the pump. But if you don't have that, the one thing you have that you can change your pump around with is the size of the impeller. You can actually go in and grind the impeller down a little bit or purchase a different impeller to put in your pump. Okay? And there's a little equation that'll tell you what the effects of that would be, and that's on page 132. So if you change the diameter of your pump impeller, you can predict how that will affect how the pump acts, okay? And it's shown with that equation. What you do is you take the ratio of the impeller diameter, and you can use that to predict the new flow, the new head, and the new horsepower that the pump will have. Okay? So those are called the affinity laws. They're used just to predict what small changes in impeller diameter will do to your pump. All right, I think we're on page 133 for just an example of that, then we'll call it good here. So on page 133, let's see what would happen if we took a 16-inch impeller out and put in a 15-inch impeller. Okay. So if we have 4,000 gallons per minute for our 16-inch impeller, if we replace it with a 16-inch impeller, we just would multiply that by 15/16. And what we would get would be 3760 gallons per minute. Okay. If we're developing 200 feet of head with the pump, which you can convert that into pressure if you want, you just multiply by 0.433, so that'd be about 86 or 87 psi with that pump. You would just take the ratio of the diameters and square it, multiply it by 200, and what you're going to get is 176 feet. So instead of 200 feet of head, you're going to get 176. Now you might wonder, why do I want less flow and less head out of a pump? Well, the answer is in the power you're going to use up. Okay, so if this pump is currently using 250 horsepower, if you take 15 over 16 and you cube it, take it to the third power, and multiply it by 250, you're only going to be using 206 horsepower. So if your pump is oversized with a 6-inch impeller, or excuse me, a 16-inch impeller, you can put a smaller impeller in it, and instead of delivering 4,000 gallons per minute at 200 feet ahead and using up 250 horsepower, you can reduce what the pump does if that's what you want. You can take it down to 3760 gallons per minute, 176 feet, and 206 horsepower. Okay? So you can predict with these, they're called the affinity laws, what the effects of changing the impeller diameter or changing the RPM would be.
Now, my question there would be, could you just put a smaller motor on without changing the impeller?
Smaller motor, you're going to get less horsepower. Yes, I think you could. This might be a cheaper fix. You know, it's just dependent on what you've got available.
Yeah.
This will tell you the two effects this thing tells you about is motor RPM and also the impeller size. So I have seen pump curves, which is a kind of a data about a pump that you get that'll have 3 or 4 different impeller sizes on it. You can buy a pump with different size impellers. And so they do affect the performance. Okay. All right. All right. So okay, that homework for sure is due Wednesday if you haven't turned it in yet. And I'll get that other homework back to you on Wednesday too. I'll get you a test review on Wednesday also. Okay. So we good? We got any questions on things? No.